Okay, everybody's back. So now we start a new chapter on planning. So I just turned on the video recording. Oh, the planning module is here. Okay. So here's the overall architecture. We now move from control to planning. A little bit out of order because I wanted to give out the assignment. So I discussed control first. So in this picture, we saw this planning part with path generation and speed profile generation. So there's a hierarchy of planners. Highest level is mission planning, which is map level navigation. Next level is behavior planning, choosing a behavior based on environmental conditions. Local planning, which includes path planning and speed profile generation. It generates a reference trajectory to be tracked by the controller. So last time we saw in this lab assignment, the reference trajectory is the circular track, which or a straight line track. And then you don't need a planner module because it's given to you. But in reality, you may need to have a local planner to plan trajectories for, say, passing a vehicle or taking a turn and so on, where you don't have a clear reference path as a track. That's where the planner comes in. So let's first look at the mission planner, which takes as input the current goal, detailed roadmap, and vehicle position, and gives out a mission path. So the mission planner is to find the optimal path for navigation from start to goal on a weighted graph. So, for example, you are trying to go from a start point to an end point, and then you have a graph of connected segments of road forming. So you need to pick a path with the least cost. So here's a weighted graph, and then this path 15790 is the shortest path. So it's also called route planning. Just like when you want to drive from UMU to Stockholm, you need to pick a route. So the approach is typically graph search algorithms like Dijkstra's algorithm and A*, and so on. So the map representation could be a geometry-based or grid-based. Geometry-based is when you have the shapes of all the obstacles. Grid-based is when you divide up the area into grids. It could be divided into uniform grids or could be non-uniform grid sizes. That is, the grid is more fine-grained near the obstacles. So to represent a grid map, you can use a two-dimensional matrix, where 1 indicates obstacle and 0 indicates free grid. And then given the grid, you can select a connectivity. Could be 4 or 8 or 16. So if it's 4, then you can travel up, down, left, right. If it's 8, you can perform diagonal travel direction. If it's 16, you may travel to further away grids, like from here to here directly. So each one is uh, more and more fine-grained, with more and more flexible travel directions. So for each given connectivity, we can construct a graph representation of the map. So given a map, if you recall from your college days, you learn about the BFS and DFS. Breadth first search starts at each node. At each node, you expand all its neighbor nodes at the present depth prior to moving to the nodes at the next depth level. For example, for this graph, you're starting from node A with BFS. You're traversing it like this. At every depth, you exhaust all the nodes and before you move on to the next depth level. For DFS, depth first search, at each node, you expand as far as possible along each branch before backtracking. So you go down all the way to the end of the path, and then you backtrack to the next branch, and then you backtrack, up to here, and then finally you backtrack up to D. Uh, so these are well-known algorithms which you learned before, so I won't discuss their details, just to mention them briefly. So they are inefficient for the traversal on the weighted graph because they do not consider edge costs for selecting the next node to expand. However, among these two, BFS is still better than DFS for path planning. BFS can finish after finding a path to the goal with total cost less than or equal to cost of all other partial paths. Then it's not possible to have a shorter path than the one you have just found. You can stop. But for DFS, you can never be sure. Once you reach the goal, you have another area of the graph you haven't traversed. So you must traverse every single node, expand every node in order to make sure that the path to goal is the shortest. So in that sense, BFS is better, but still both are inefficient because their traversal is not dependent on edge weights. So they're not used for robotic path planning. So I show them here only for comparison purposes. So I have this running example from start to goal. You have this graph with weights like this. So you need to find the shortest path, which is this path. Yeah, I think I had a typo here. Start to goal. So for BFS, you start from S, and then you expand A, and then C, and then B, and then G. So from the top path, so I use the color blue to indicate uh, the uh, the node that has been traversed already. So this here B should be blue because it has been done. So okay, D to A to A, C, B, B. After B, you have G. So you traversed this path. But at this point, you have traversed the top path. But then you should come back to C, and expand C to reach G from C. So because at this point you have found a path with length 25, but the other in the other node C to be expanded, you have a partial path with length 10. So you're not sure if this partial path may turn out to be a better, shorter, complete path. So you must not finish after you reach G from B. You must continue to expand C, and then you found a path with length 22, which is shorter than 25. So you finish here. See, I think I didn't write it correctly. Must expand node C. Total cost greater than 10. Yeah, that's right. So at this point, after you reach the goal, you should continue to expand C to find the shortest path. So for DFS, you start from S, you traverse A, and then B, and then G, and then you traverse the other branch, backtrack to traverse C and then G. After you traversed all the nodes, expanded all the nodes, you can find the shortest path. So Dijkstra's algorithm works by taking into account the edge weight, the edge cost. So it keeps track of an open set and a closed set. So you push a node into an open set and pop it one by one. So if it reach the goal, you extract the path. So notice here, if you reach the goal, you can stop. And then if you haven't reached the goal, you look at all the successors and skip all the closed nodes and take the open nodes, that's the nodes that haven't been traversed, and then get the edge cost. If the cost up to now plus the edge cost does not exceed the current best cost, less than the current best cost, you save this new cost as the current best cost and add U as the predecessor of V. Otherwise, you push push it into the open set. So let's look at an example. So here's the running example. You start from node S, cost to S obviously is 0 because you are at S. And then you expand the A and C nodes with costs of 2 and 10, and then you push them into the open set. So the open set now contains 2 nodes, A with a cost to S as 2 and C with cost of to S as 10. And then you continue to expand A because it has a lower cost. So in this pseudocode, the pop is based on a sorted list based on sorting by cost to the origin, to the source. And then you expand B, you find out the cost to a source is 5. Now S and A are both closed. And then you expand C because B has been expanded, and G, here is G. G is added, but G has cost of 25, so G is behind C. You must expand C first. And after you expand C, you get 22 as the cost to S. And then you can finish. Calling the extract path, because you saved the predecessor of every node while you were traversing, you can simply extract all the predecessors of each node. You get the shortest path S to C to G with the cost of 22. So the dexterous algorithm expands the nodes in the order of decreasing cost to source. So that's why it tries to find the shortest path. A star algorithm, I put them side to side. A star on the right has this extra term, a heuristic function, which is added to the path cost, and then you compare it to the current best. And if it's less than the current best, you save it. Yeah. So the H function is the estimated cost to go function. That is, you're estimating how much additional cost you're going to incur before you reach the goal. So it's a heuristic function because you don't know exactly how far what the cost to go is. If you did know exactly, then you probably have solved the problem. You can only provide the estimate. So the H, if it's equal to 0, then A star becomes Dijkstra. So let's look at the example here. So starting from node S, suppose the heuristic cost to go function says HS is 11.5. Actually, HS doesn't matter in this context. But when you move to node A and C, the H function comes into play. So suppose at node C, you have the heuristic function that says from C to go, I estimate the cost to go is 10.5. It's actually 12, but I don't know that. I can only do an estimate. From A to go, you can estimate the cost to go is 22.5. It's actually 23. So the estimate must be an underestimation for the algorithm to work. So then at A, the estimated cost, total cost is current cost to the source plus estimated cost to go, which is 22.5. And then A's total cost estimated is 24.5. C's total cost is 20.5. So C is ranked as before A, and C should be expanded before A. Now you expand C. Now you reach the goal. So cost to go now is 0. You don't have to do estimation anymore. And then the total cost is 22, length of this path. And it's less than the other path estimated total cost of 24.5. Now you have finished 2 steps. So extract path yields the S to C to G path. So it looks to be a very fast algorithm. Now, what happens if the heuristics is inadmissible? That is, if you did not always underestimate the cost. So suppose here you have overestimated the cost to go function. You estimate the cost to go is 15.5, where the actual cost to go is 12. Then what happens is that you should expand A, because A has a lower estimated cost. Yeah, I think I should put A before C. Yeah, I'll do that later. So uh, and then you expand A to reach B. Suppose HB is 19.5, and then you get a total estimated total cost of 24.5 at B, at 5 plus 19.5, which is less than C's estimated cost of 25.5. And then you continue to expand B to get a total cost of 25, SABG, which is less than the estimated cost of going through C, which is 25.5, and then you get a path of SABG, and you think it's a shorted path, but it's incorrect due to overestimation of the cost to go function from node C. So after finding the path S to A to B to G with length 25, we incorrectly ignore the other path through C, since its estimated total cost 25.5 is more than 25. So with admissible heuristic like underestimation, HC is 10.5 less than 12, we can either directly find the shortest correct shortest path going through C with length 22 and correctly ignore the other path through A and B as shown earlier. Or we can find the path SABG with length 25 due to the even stronger underestimation of HA and HB, but then we must continue to expand node C to find the correct shortest path SC to G, since its estimated total cost of 20.5 is less than 25, so there is a chance of shorter paths through C. So after we find the upper path, we cannot stop. We must continue because the other path has a lower estimated total cost. So in either case, we will find the correct shortest path of SCG. But with the incorrect, inadmissible heuristic of overestimation, we may find the incorrect path. So with the admissible heuristic, where HV is less than or equal to actual cost to go, if we find a path to go with exact cost V less than or equal to estimated total cost of all the other paths, we can finish and safely ignore all the other paths, since their actual cost must be higher than V. But with an inadmissible heuristic, HV with no guarantees, with either greater than or less than actual cost to go, if you find a path to go with exact cost V greater than or less than estimated total cost of all the paths, we cannot finish. I should say less than. With this one. So we cannot finish and safely ignore all the other paths, since their actual cost must be lower, may be lower or higher than V. Okay, so it is clear. So the point is that for a star algorithm to work, the heuristic function estimating cost to go must be an underestimation. So how do you design a admissible heuristic? So in the Wheelie graph representing the road network, edge cost may be travel distance or travel time, taking into account factors such as speed limit, traffic congestion level, and so on. So an edge may be undirected for a two-way route or directed for a one-way route. So if the objective is to minimize the total travel distance from start to goal, the edge cost is travel distance between two locations. We can set a heuristic function h to be the straight line distance to goal. Then h must be an underestimation. If the objective is to minimize the total travel time from start to goal, then the edge cost is travel time between two locations. We can set HV to be the straight line distance to goal divided by the maximum speed limit. So that's the shortest possible time you can take to travel to goal. So that's also underestimation. So here's an exercise from start to target to go. You have the edge costs and also the coordinates in the Cartesian coordinate. So you can compute a heuristic function uh, by uh, by taking the straight line distance between any 2 points. For example, the straight line distance from here to here is 2, and from here to here it's 2. Yeah, from here to here it's 1 plus 1 square root. So that's your heuristic function. So you can work it out as an exercise. I may give out a exam question like this. So A star versus Dijkstra's algorithm. So in this figure, the red crosses denote obstacles and green circles denote explored positions. So you're starting from the start position, you're trying to get to the target while avoiding collision with the obstacles. So here's the A star algorithm with a good heuristic. Here's the Dijkstra's algorithm. So Dijkstra essentially explores in every direction, so it's very inefficient, whereas A star explores in a very directed manner because of the guidance by the heuristic function of cost to go. So here's the animation of Dijkstra versus A star. So A star is exploring in a more directed manner. So if you look at closely, it's reaching the goal faster than Dijkstra. There we go. And Dijkstra is still going. Finally, Dijkstra finishes after exploring almost all the area. So because it's an undirected search, it's not aware of where the goal is. Whereas A star is a directed search, so it's trying to minimize the cost to it's trying to reach for the goal. So in this link, you may find additional animations you can explore yourself. So another animation, A star and Dijkstra. So A star explores a smaller area. And here's the visualization of the path length to start position. You're starting here, the length is 0, and then you're reaching the goal here, and you can explore fewer nodes based on A star. So any questions on A star and Dijkstra? So let's move on to the behavior planner. So the goal is to plan the set of high-level driving actions or maneuvers to safely achieve the driving mission under various driving situations based on rules of the road, such as traffic lights, stop signs, static objects, parked vehicles, and dynamic objects, such as moving vehicles, cyclists, pedestrians, and so on. Need behavior prediction for dynamic objects. So driving maneuvers may include track speed, maintain current speed consistent with other vehicles on the road, follow leader, so match speed of the leading vehicle, and maintain a safe distance, decelerate to stop for a stop sign, for example, stop, remain in the current position, change lanes, do a turn, do a pass. So one approach is based on finite state machines. So you design a FSM with each state as a maneuver, and transitions may be triggered by inputs such as traffic light changing color. And this must be designed by the expert manually. So another approach is reinforcement learning based on maximizing cumulative reward. So we'll mainly discuss the FSM approach. So let's look at one example of an intersection scenario, four-way intersection, two-lane road, and stop sign in every direction. No other dynamic objects, only this one car. So you discretize the intersection into approaching zone, the red box, and at zone, the green box, and on zone, the orange box. So size of each zone is determined by vehicle speed and size of the intersection. So based on this discretization, you can design the finite state machine trigger conditions. So as you're approaching, as you enter the approaching zone, the red box, you enter the track speed state. You're performing the no, I'm sorry, outside the approaching zone, you are doing track speed, perhaps tracking a constant speed. And then when you enter the red approaching zone, you go into a decelerate to stop maneuver. And then when you enter the green box, the at zone, you should go to a stop state triggered by the velocity going to 0 and position equal to at in the green box. So to make the state machine more robust to noise in state estimation, you may change the trigger condition of at equal vehicle velocity is 0 to less than a threshold, because state estimation is often noisy. So notice that for intersection with stop signs, there's no transition from decelerate to stop back to track speed. So there's no such transition because at a stop sign, you must always stop. Whereas for intersection with traffic lights, there should be such a transition, as the light may turn green while the vehicle is decelerating. So you may not go to the full stop state, but instead transition from decelerate to stop to track speed. So all these rules should be defined by the designer. So at the intersection with dynamic objects, you need to add additional state, follow leader, to handle situation where another vehicle is in front of the eagle vehicle. So again, you can see that this is a one-way arrow, not a two-way. No transition from decelerate to stop to track speed, since vehicle must come to a complete stop at a stop sign. And if you have multiple scenarios, you can have a hierarchical state machine where each driving scenario is modeled as a superstate, which contains a lower level state machine for the scenario. So for example, you have the intersection finite state machine, and then you have a single lane drive lanes scenario, and you may have another multi-lane scenario with a merge lane state added. And then you may transition between different scenarios. So that's a very brief description of behavior planner. I skipped a lot of details. For example, if you have dynamic objects, other dynamic objects, you need to perform prediction of their movement, which is a very difficult problem. So especially if you have pedestrians, which are very unpredictable. So for example, if you see two pedestrians talking on the sidewalk, then it's very likely that they will remain on the sidewalk. You don't have to worry about them. But if you see a pedestrian waving to another pedestrian on the other side of the road, then it's very likely that the pedestrian is going to cross the road. So you must be careful. So that's the behavior prediction problem, which is very difficult, which involves a lot of machine learning, deep learning. So let's move on to the local planner. So the goal is to generate a feasible, which is a smooth and collision-free trajectory. For example, here is trying to change lanes in the presence of two other vehicles. Some trajectories result in collision. So this is a collision to the sidewalk. So these two are out. And then the others, you should do a ranking based on objective function to select the optimal trajectory. So it's decomposed into path planning and speed profile generation. So this shows the path, but actually you should have a speed profile on the path because it determines if the trajectory is safe or not based on the surrounding vehicle's speed. So local planning is also called trajectory planning. It includes a path planning and speed profile generation. Path planning, you can use graph search algorithms such as Dijkstra's A-star, hybrid A-star, and sampling-based algorithms. We'll introduce two of them. And we'll talk about path planning for parking and then generating smooth paths and speed profile generation. And finally, we'll discuss a few approaches for combined generation of path and speed profile. So optimal control or MPC may be used here for generating trajectories. So MPC may be used for tracking existing trajectory, or it may be used to generate a trajectory. But we're not discussing this here. So limitations of A-star and Dijkstra's algorithm for local planning. So both are discrete methods. You are traversing a discrete graph. They do not consider kinematic or dynamic constraints. So a vehicle cannot move sideways directly, except some specialized vehicles. And turning angle is limited within a range. So for example, if the vehicle's heading is north, and the path planner says going right, go right, then the vehicle needs to make a long turning motion to go to the right grid cell. So for hybrid A-star, it tries to generate smooth paths. So it uses predefined motion primitives to get reachable states and construct the search tree. So the resulting path is smooth and kinematically feasible. So a motion primitive is a realizable translation and rotation in a time step under maximum acceleration and speed constraints. And distance traveled is large enough to leave the current grid. And curvature is constrained by maximum turning angle, and orientation change is integer multiple of discrete turning angle step size. So here's the regular A star. You have 6 possible movements to the next grid cell. 8 possible movements. And then hybrid A star uses motion primitives to generate 5 possible next positions, which falls into 2 possible grid cells. So all the other white grid cells are not feasible, so they're ignored. So for A star, you may generate a path like this with straight lines connecting discrete points, but it's not feasible kinematically or dynamically. No vehicle can make a turn like this. So for hybrid A star, you generate a much smoother path to the goal. So so it's used by Stanford University in the 2005 DARPA Grand Challenge for the local planning. So a comparison of A star and hybrid A star. A star state representation is discrete location at each grid point. And hybrid A star is continuous pose of the vehicle, including its x-y position and its heading angle theta. So search expansion strategy. So in A star, every neighbor grid is a search node. So at every point grid cell, you have 8 or 16 possible next choices. For hybrid A star, you are based on predefined motion primitives. So so multiple search nodes may exist in the same grid. So here we have 4 points possible positions in this one grid, but 1 possible position in the other grid. And then you must explore every one of these 5 positions in the next step. So A star is complete and optimal, but hybrid A star is not. So it may not be guaranteed to find a path if one exists, and it may not find the optimal path in terms of total path cost. So here's a quiz. Which of the following statements are true for Dijkstra's algorithm, A star, hybrid A star, respectively? So Dijkstra's algorithm, only C and E are true. So it always finds a path if one exists, and the paths it finds are guaranteed to be optimal. It's the shortest. While A star has additional B, it uses a heuristic function to guide node expansion. Hybrid A star is A, B, and D. So it's a continuous method. It uses a heuristic function like A star. The paths it finds are guaranteed to be drivable because the motion primitives are feasible by definition. However, it's not complete nor optimal. Therefore, C and E are both false for hybrid A star. Questions? So let's look at the RRT, rapidly exploring random trees. So it's a sampling-based method. So you start from a start position location S in the tree, and you're trying to reach the goal location. So you generate a random point in this area. Say a random point happens to fall in here. That's the point. And then you'll find the point P in the tree that's closest to R. In this case, the tree is has only one point S. So this is the only point P. Then you add a branch of predefined length from P in direction of R. So from here to here, you add a branch. If a new branch intersects the obstacle, you discard the new branch or shorten it. So in this case, you're expanding the tree 1, 2, 3, 4, and then at the other point 5 is intersecting the obstacle. So you don't add this branch, you discard this point. Then you sample a new point in here, and then you connect it to the closest point in the tree, and it doesn't intersect obstacles, so it's feasible. So finally, once you reach the goal, you can compute a path from start to goal through the tree. And by adding shortcut path, you may shorten the path. So for any points in the path, add direct line unless direct line intersects obstacle. So here in this example, eventually you have explored these points. Eventually, you find this path, the red path. So you may smooth it by iteratively sample points between nodes on the overall path and then checking if 2 points could be connected to reduce path length. So now finally you get a green path because you found out there are shortcuts you can take. So so here's this is RRT. Here's the animation. So here I set a start location, but I didn't set a goal location, so it doesn't stop. It just goes on forever. You can see how the tree is grown. Eventually, it'll cover the entire area. So eventually, it'll reach any goal. So the typical growth process looks like this. Gradually, it'll be like this. It'll cover every point. So here's the animation of a RRT in action. You start from this point here, and then you generate random points, random locations. If you can connect it, you connect it. Otherwise, if you intersect an obstacle, you discard it. And eventually, after enough sampling, you can get around the obstacle and find a path. Yeah, it's a little bit slow. So a PRM, probabilistic roadmap, is a somehow similar to RRT in that it's also a sampling-based method. So it works in 2 steps. The first step is to construct a map. While number of points in roadmap is lower than threshold, sample a random point. If new point is not in collision with the obstacle, connect new point to all other points in the roadmap with lines, as long as they do not intersect obstacles. So this figure shows the map construction process. you can see it gets a very dense graph in this area, avoiding all the obstacles, the blue parts. So path finding is to connect a start location to nearest point in roadmap uh, such that connecting line does not intersect any obstacle. And then you do the same for the goal location. Connect it to the roadmap. And finally, you will find a path between start and goal locations, traversing the roadmap with algorithms such as A star or dexterous. So this figure shows the map construction process, but the next path finding process is not shown here. So with RRT, every time a new start goal locations are given, an entirely new graph must be generated, which may be inefficient. But for PRM, it builds a roadmap graph for traversing through a region, but relies on A star or Dijkstra's algorithm to find the shortest path from start to goal, traversing the roadmap. Hence, the roadmap is reused each time a new set of start goal locations are given. So if you're constantly replanning to a new location, then PRM is more efficient. So PRM and RRT make no guarantees. So there are many variants of these two algorithms, and many of them are probabilistically complete, which means that if a path exists, it'll be found in finite time, but in the worst case, solution time can be very long, longer than exhaustive search. The reason it's longer than exhaustive search is because it's a random sampling method. So there is a small chance that you're just unlucky and all your sampling points are in the wrong locations. And then it may be possible that you take a very long time to reach the goal. And also, there's no guarantees on solution quality, so it may not find the shortest path. So with PRM, A star and Dijkstra is guaranteed to find the shortest path for the given roadmap, but the roadmap may not be optimal. So therefore, the overall algorithm does not guarantee solution optimality. And also, they may need post-processing to make it more smooth. So here's the quiz. Which statement is true for RRT and PRM algorithms? So both algorithms will produce the shortest path without post-processing. That's wrong. Even with post-processing, it's still wrong. So yeah, I can make it stronger. So both algorithms can be used for high-dimensional spaces. Yes, robotic motion planning, such as the robotic arm, the space may be very high dimensional, but for mobile robot planning, it's typically low dimensional. 3 for ground robot, that is position and heading, and 6 for aero robot. That's position, XYZ position plus yaw, roll, and the other one. So yeah, so C is not correct. PRM always generates a better path. That's not true. And D, the time for computation is consistent and predictable. That's also wrong. It's unpredictable. So the next topic is path planning for parking. I'll introduce Dubin's and Reed's shape curves, but I won't go into details on how they are generated. So both of these curves consist of straight lines and arcs with maximum diameter. So Dubin's vehicle can only drive forward. Reed's shape vehicle can drive both forward and backwards. So here's a problem of parking a car. You start from the red position. You're trying to reach the green position while respecting the kinematic constraint of a bicycle model. So Dubin's curve is forward only. So starting from a red position, you are driving forward and trying to get into the parking spot. It's published in a paper in 1957. For the Reed shape vehicle, you can drive forward and backwards. Therefore, you can drive forward and then back up, which is how people drive in reality. So you can compare Dubin's versus Reed shape from the start position to the goal position. You can change the start and goal, and the red is the Dubin's curve, and the black is Reed shape curve. So Dubin's is almost always longer than Reed shape because you cannot back up, but sometimes they're the same. So the tuning, the adjustment is on the vehicle's pose. So here's the problem of parking with obstacles. You have a black obstacle in the middle. So for obstacle-free case, both Dubin's and Reed shape always can always find a solution. But if obstacles exist, then Reed shape always finds a solution, but Dubin's may not. So that's a path planning for parking. Now let's move to the topic of generating smooth path. So a path can be represented as a sequence of points, such as A star, dextrous, and PRT, PRM. Or it can be represented as a smooth parametric curve that satisfies boundary conditions at two endpoints and also constraints on curvature and optimized objective function. So here's a two point start and end goal location. Start, you have to have a pose of x, y, theta, and curvature k0 kappa 0, and goal of xf, yf, theta f, kappa f, where kappa curvature is inverse of the radius of rotation. If you recall, in the kinematic bicycle model, the rotation around the instantaneous center of rotation. So obviously, a higher curvature makes it harder to track. So and that's the two endpoints. And then you must ensure that every point on the path, the curvature must not exceed a maximum upper bound to satisfy kinematic dynamic constraints and to improve rider comfort. So if you're riding a vehicle that's turning tight corners all the time, it's not very comfortable, and it may not be kinematically or dynamically feasible. So one approach is quintic spline. So you model the path as a fifth degree polynomial with closed form solutions for boundary conditions. So x u is just a u is uh, artificial variable to in the artificial parameter in the function. So so xu is this fifth order polynomial, same as yu, and you start from the x0 y0 to x1 y1. So so it has a closed form equation, but the drawback is that the curvature along this path, along this polynomial curve, and its derivatives may be discontinuous. So this is the formula for getting the curvature at any given point on the path, which I'm not explaining the details. But the point is that may not be continuous at every point. So another approach is polynomial spirals. So now we start from a polynomial expression for the curvature. Typically, we use a cubic polynomial. So by definition, the curvature curve is smooth and never discontinuous. Therefore, constraining a few points along the path, the curvature, may be enough to constrain the entire curve. So path is modeled based on the curvature function. So you get a theta as integral of the curvature, and then you define the xy positions along the path based on theta. So this is just geometry. So the pro of this approach is that the curvature function is smooth. The con is that now the path has no closed form solution. Needs to be computed with numeric integration using Simpson's rule with high computational overhead. So Simpson's rule is to compute this kind of derivative with an approximate expression like this. That's for computing these two expressions for x and y. Whereas for the previous spline,
Men ska jag hämta honom med bil?
yes?
What?
Sorry,
sorry, I didn't mute my button.
Okay. So yeah, if you compare these two, they have exact opposite pros and cons. So cubic spline has a closed form equation for paths, but not for curvature, whereas spirals have a closed form expression for curvature, but not for paths. So here's an example of cubic spline for the xy position. Here's an example for cubic spiral. So yeah, eventually they look similar, but for spiral, you must perform numeric integration to get the curve. So objective function, let's take the cubic spiral case. So you may define an objective function of minimizing the bending energy, which is defined as the integral of squared curvature along the path in order to distribute the curvature evenly along the spiral. So it's mainly for driver comfort to make the path smooth. So this expression and its gradient have closed form solutions based on the spiral. Subject to constraints, one is the endpoint constraints at the two endpoints, and also the curvature constraints for two intermediate points. 1/3 of the path and 2/3 of the path. It's because the curvature equation function is smooth. So if we constrain these 2 points, then this smooth function, the spiral, will ensure that every point along the path, the kappa max constraint is satisfied. So that's a key advantage of the spiral approach. That is, you don't have to constrain every point on the path, only a few points for the curvature. So conformance lattice planning is a approach exploiting the spiral approach. So here's the problem. So you have a start position. Suppose the vehicle is at this xy location, xy position, and you're traveling along this this road. To plan a feasible collision-free path to the goal, you exploit the road structure and generate a set of lattice paths laterally offset from a goal point along the road. So the goal point is dynamically calculated based on the speed and other factors. So you may have a look at horizon, which longer look at horizon improves ability of collision avoidance, but increases computation time. So here's the endpoint. This golden point. Here's the goal point, and then you sample the additional endpoints, the blue dots, with lateral offsets from the goal according to vehicle heading. So you sample these points, and based on maximum vehicle heading, suppose you're not supposed to turn very sharply on the road, so you may have a range of vehicle heading, a heading angle. So based on that, you generate all the other endpoints. For each endpoint, including the goal point, every point you solve the optimization problem to get a spiral based path, a spiral for the curvature, and then use numeric integration to generate the path. So for this example, you start from this point, and then you generate a set of paths to the goal point as well as to the other endpoints within the look ahead horizon. So the reason you want to do that is for collision avoidance. So for example, if you had a vehicle that's broken down and parked in the middle of the road, the red box, so you can check for collision for every point along each path. So you can see that the red paths have a collision with the red obstacle. So you can remove them, and among the remaining collision-free paths, you select one based on custom objective function, such as maybe we choose the blue path. The objective may be perhaps we prefer paths close to the center of the road while penalizing a path that come too close to obstacle. So that's collision checking and path selection. And repeat this process for each planning period in the receding horizon manner. So every time you move one step forward, one time step forward, you redo the process, similar to MPC. And then for this case, the full path that you actually traverse will converge to back to the center of the road after passing the obstacle. the blue line. That's the final path that you have generated based on the lattice planner. So any questions on the lattice planner? So here's a quiz. Which path consists of continuous segments? One is a track straight line segment. One is track waypoints. Three is track parameterized curves. And none of the above. So parameterized curves consists of continuous segments. These curves provide the benefit of continuously varying motion and can be constructed to have smooth derivatives to aid in the consistency of error and error rate calculations. So by making the path smooth, you're making the job easier for the downstream controller to track the path. So now, up to now, we have discussed path generation. So how about a speed profile for a given path? Uh, so now let's look at how to set reference speed. It comes from a high-level behavior planner. So maybe based on current road speed limit, maybe based on current maneuver, such as stopping due to stop sign or red light, or following a lead vehicle. So for the following lead vehicle case, the time to collision can be computed with this equation, assuming a constant speed for the eagle vehicle and lead vehicle. So you need to reach the red point at the lead vehicle speed to avoid collision. So and also you may have additional constraints such as the curve due to curvature. So the curvature is related to a velocity and acceleration in this equation. So curvature is 1 over r. Yeah, it's a lateral acceleration. So, and then based on all these constraints, including the uh, road speed limit, the driver maneuver, and the curvature, you take the minimum among all these upper bounds to be your reference velocity. So here I show two possible speed profiles. One is the linear ramp profile, which is constant acceleration to reach reference speed. This may be you're starting from a parked position, or you may be merging into a highway, for example. The other profile is trapezoidal profile, with a constant deceleration followed by zero acceleration followed by constant deceleration to zero. So for example, maybe for stopping at a red light. So for a linear ramp profile, you can compute, given a path length s, initial final speeds v0, vf, you can compute the required acceleration. I have some explanation in the next slide. Yeah, I should move it here. Yeah, I'll do it later. So and you may clamp the acceleration to improve rider comfort by putting an upper bound on the acceleration. And then for each path arc, each small arc, you compute the speed using accumulated path length to origin to the current position up to that point to generate a speed profile based on the equation here. So this is derived from the this equation. So for the trapezoidal profile, you divide the path into 3 segments. The first is a constant deceleration, where you are trying to decelerate from a velocity v0 to a vt, the transit speed. This is vt. So to help you understand this equation, have this here. So consider a robot with starting speed v0 and constant acceleration a0. After time t, it reaches a speed of v0 plus a0t and traverses the distance of time t times the average speed, which is v0 plus vt divided by 2. And then if you plug in the t from this equation, you get this equation. So that's where this comes from. So the distance traveled, SA, can be computed based on the starting velocity v0, the transit velocity vt, and the acceleration. And then for every point, every little arc on this path, you compute a speed profile for I, where I may be 1 to n, based on this equation, basically forming a straight line. So for second segment, the speed is constant. That's easy. For the third segment, you do the similar thing, except for the final speed is 0. So the final expression for the velocity profile is that less than SA, where SA is defined in this equation, you have this form, and in the middle you have this VT, and in the last segment you have this. Okay, so that's a trapezoidal speed profile. So any questions so far?
I guess the use of this trapezoidal profile is to reduce the speed so you can stop if there's some urgent need for stopping or something.
Well, it's not an urgent stop because you have a constant speed segment in the middle. So it's more for when you see a stop sign or a red light from a distance, and then you gradually, smoothly stop. So artificial potential field is an idea of the both path and velocity, the trajectory generation by constructing a smooth potential field function where higher values for the function when the robot is near obstacle and lower values when it's further away, and the lowest value at the desired goal location. So the robot's travel direction is based on gradient descent on the potential field function leading to the goal location. The drawback is that it may be stuck in local minimum. So this example is taken from the Coursera robotics course on computational motion planning. but it's specialized for drones, for aero vehicles, but which is more complex than a ground vehicle. So here's a consider a point robot moving in 2D. So you have a start location and you want to go to this goal location. And you have the obstacles, they're shown in black. So you design an attractive potential field with the goal location G with the lowest potential energy, potential value. And then you have the repulsive potential field around every obstacle. Notice that it gradually drops down. So even though you're close to an obstacle, it tries to repulse you away. And then addition of these two curves, you get the combined potential field like this. So your starting location is here. Imagine it's a ball rolling down the hill. It'll naturally avoid the obstacles and seek the low points on this surface, eventually reaching the goal location. So it's a very intuitive method. So let's look at, these are just example definitions of the artificial potential field functions, not necessarily always in this form. So for example, you may define the APF to be proportional to a squared distance to goal. At the goal, it's 0. And before you reach the goal, the further away, the higher the potential. And repulsive potential field, you may define a function like this. So if the distance to the obstacle is less than equal to a threshold, if the rho is less than equal to the distance to the closest obstacle, which is d0, then you have this form, and 0 otherwise. So d0 controls region of influence of the repulsive potential. Region of influence. So you can see that if it's exactly equal to d0, then it's 0. If it's if rho x goes to 0, it goes to infinity. But in reality, you put a cap, put a upper bound on it. So if you define the potential function as in the previous slide, then you can set the travel direction based on gradient descent. So the potential function derivative, take the derivative of x1, x2, and take the negative. That's the direction of travel. And the travel speed is determined with speed profile generation method. So here's the two example trajectories. If you start from this point, and you have the arrows are gradient descent directions. Imagine a ball rolling down a hill. You'll eventually go this path. If you're starting from this point, it rolls in this way. So here's an animation. So it naturally avoids the obstacles. And this website is very good. So it has maybe 100 implementations of various algorithms for robotics. So and then the dynamic window algorithm is a widely used approach for trajectory planning for autonomous vehicles. So the traditional planning is in configuration space. if we have a point robot, it's a Cartesian space. But DWA performs planning in the velocity space. That is the angular velocity and translational velocity. For example, if the angular velocity has a range from -90 to +90, that's on the x-axis, and the translational velocity has range 0 to 90, that's on the vertical axis, then you have this two-dimensional velocity space. And you plan in this space, not in the configuration space on the left. So for example, this dark region indicates collision regions. So this means that with high speed in this area, and the angular velocity is also pretty high, then you may run into right wall 1. That's a collision indicated by this region here. It means that in this region, the combination of V and omega is infeasible. In this region, a right wall 2 region, it means that if you have a high velocity, translational velocity, with a small angular velocity, you may run into the right wall here. So that's also a collision situation. So in this V omega space, you can mark out the regions which are infeasible, and regions, white regions are feasible regions. And then you plan in this space. So recall the kinematic bicycle model. So it's performing a circular motion around ICR, and the next state at t plus dt may be in collision with an obstacle. So so to avoid collision with obstacles, you can compute the velocity constraints on v and omega. So suppose dist is the distance from trajectory to closest obstacle. And then these are the bounds on the translational and angular velocities. So VB dot is the maximum braking deceleration for V, and omega B dot is the maximum braking deceleration for omega. So the proof is similar to what I showed before. So suppose you have a robot with starting speed V and constant acceleration or deceleration minus VB dot to go to speed 0 at time t, you can compute the distance as this equation here. So to avoid collision, you can constrain the distance, the actual distance, to be greater than this value. Therefore, the vehicle the robot can stop before reaching the obstacle. And here's the upper bound on the velocity. That's where this equation comes from. Similarly for omega. So also you may have limited acceleration range. So acceleration range may be from minus AV max and plus AV max for translational velocity, and minus A omega max and A omega max for rotational angular velocity. And then if you have these bounds, you may compute the the velocity ranges, lower and upper bounds, to be VA minus the maximum deceleration times dt, the time step size, and upper bound is the VA plus this value. Similarly for angular velocities. So the A omega max may be obtained from the constraints on the delta, the maximum steering angle, and V max, the vehicle's maximum speed. So these two bounds may also be constrained to improve rider comfort. So as a result, centered around the current velocity, you have somehow my PowerPoint has a strange effect of when I draw something. So you're centered at this time step, current time instant. You have this velocity here and angular velocity here. So that's your current point in the v omega space, the speed space. And then within the time step length dt, based on these formulas, you get a box of constraints on the v and omega in the next time step. So that's why this algorithm is called dynamic window algorithm, because the v omega is constrained within a window that's dynamically changing all the time at every time step. So here I wrote that the maximum deceleration seems to be the same as the minus VB dot minus omega B dot, but the paper puts them as different constants. So I'm not sure why. So also the last constraint is the translational rotational velocity constraints imposed by perhaps the vehicle's performance reasons, or perhaps by the speed limit or some other reasons. So by combining the three, VA is the if you recall, VA is to avoid collision with obstacles. So VA is this a gray area, except removing the dark areas. That's the collision area. And then VD is the area based on the current position in the V omega space and the maximum acceleration. So that's the box around the current point. And finally, VS is the large box, the absolute bounds on the V and omega. So the final feasible region is the intersection of these three regions. That's the white area. So in this case, the VS has no effect in the figure, but it may have an effect in general. For example, if you're moving close to the boundary, so maybe your the box is here, so you may need the Vx to clip the box to keep it within a given range. So we have obtained the this white area as the feasible V and omega in the next time step. Then you can choose a trajectory from among the feasible trajectories. that is from within the white area, you may choose a trajectory by maximizing objective function. Maybe one defined like this. So heading is the maximum if robot moves directly towards the target. So for example, here's the robot's current position, and this is the predicted position at t plus dt. At this point, if the target is here and your heading is here, then the theta is the heading relative to the target. So the smaller, the better. Clearance is the distance to the closest obstacle on the trajectory. The larger, the better. And speed is a forward speed. The larger, the better. And then you combine these with a weighted sum and maximize the overall function to pick an optimal trajectory. Notice the three terms have different units, so you should normalize them before summing. So the set of feasible speeds to avoid collision with obstacles, the VA, if it cannot be determined analytically, we can adopt a sampling-based DWA. So for each planning period, you perform equidistant sampling from vehicle speed space, VD and VS, to get a set of speeds V1 to Vm, omega 1 to omega m, and then get m squared pairs of V omega I by pairwise combination. And then for each one of the V omega pair, you generate a set of predefined trajectories, and you check for collisions and remove the infeasible trajectories that result in collisions. Finally, you define the objective function like before and select the optimal trajectory. So this is the figure I showed before of a passing maneuver. So this is how the DWA plans a trajectory. So this is a very widely used planning algorithm in autonomous driving. The planning period dt, notice that it's not the control period. So the planner typically has a larger period, it runs at lower frequency than the controller. Okay, so that's the end of the planning module. I have another chapter on Intel's RSS, which I'll discuss. I think I can finish it today. So any questions on the planning chapter? Okay.
Yes, maybe I can mention before, if people have to leave, that next week I will talk about reinforcement learning, and we will run it from 1 o'clock to 3 o'clock because I have another course at 3. So you will get more information about that later.
Yes, Carla, you need to create a new recurring Zoom meeting because my reservation is only until today.
Yeah, exactly. So I will add in the schedule as well. And I was thinking about Thursday after that. That is in Sweden, it's a holiday called the Valborg. So usually some people are free from the work and so on, but I think we run anyhow between 1 and 3. I don't know what Sangwa say. Should we run in 2 weeks also?
Well, it's up to you because the video is recorded, so people don't have to attend in real time.
Yeah, so if some students have some comments, please tell me. But we plan to run for the next 3 Thursdays between 1 and 3. Okay.
Okay, let's take a 5-minute break. Let me stop the video so we have a new video next.